Hello everyone, and welcome to my channel, Software Performance Optimization. My name is Miguel Gomez, and I've been a software engineer for over 25 years. I've spent most of my career developing engineering simulation software, but early on in my career, I also spent a number of years developing computer games. As we all know, when it comes to software, faster is better. Poor performance leads to poor user experience, and performance is one of the top complaints that users always have. In this video, I'm going to talk about the most common software performance bottlenecks and offer guidance on how to deal with them. Some of these issues might seem obvious, but some of them might be surprising to even the most experienced software developers. Okay, so let's get started. Bottleneck number one is accessing the hard drive too frequently. There are definitely times when you need to access the hard drive, such as saving or restoring a workspace, or when intermediate calculations are too large to fit in memory. But transferring data to and from the hard drive is one of the slowest things you can do on a computer. Even transferring data to and from a solid state drive is many times slower than transferring to and from system memory. If you have to access the disk, try to do it in large contiguous blocks rather than reading or writing many small blocks of data. For very large files, try to load only the data you need when you need it. For large calculations, try to avoid scratch files and only do the calculations in memory. Fortunately, commonly used operating systems like Windows, Linux, and Mac OS have built-in file caching. So once a file is accessed, it gets mapped into memory, and your program doesn't have to read it directly from the disk anymore. On the other side of this, if you use software that accesses the disk frequently, a solid-state drive should provide noticeable speedup. However, adding system memory may not give you a speedup if the software was not specifically written to take advantage of that extra memory. Bottleneck number two. Allocating and deallocating memory too frequently. The very act of allocating memory is expensive. In C++, a call to the new operator using the standard allocator has to request that block of memory from the operating system. This request takes time, and the overhead of allocating even a small block of memory can be hundreds of cycles. Because of this, allocating and deallocating blocks of memory too frequently can seriously degrade performance. It's not always obvious when memory is being allocated. For example, when you copy one standard string into another standard string, the destination string has to allocate memory and then copy all the characters from the source string into the destination string. So if the scope of the destination string is within a loop, an allocation and deallocation will occur every loop iteration. Unless you have an extremely long string, the bottleneck won't be the copy, it'll be the memory allocation. In general, you should only allocate memory when it's absolutely necessary. If you only need a small amount of memory, try creating a buffer on the stack rather than allocating memory on the heap. For example, if you know a scratch array always has less than 1,000 elements, you can safely make that array a local variable. If you must allocate memory, allocate it outside of loops and reuse it as much as possible. For example, if you need an array to hold the results of an intermediate calculation, allocate that array at the widest scope that is reasonably possible, and then reuse that array as much as you possibly can. This will help amortize the cost of memory allocation and initialization. In addition to the cost of memory allocation, there's also a big cost in initializing that memory for the first time, what I've come to call the first touch penalty. When memory is allocated for the first time, its virtual pages have not yet been committed to the operating system, meaning that the virtual addresses have not actually been mapped to physical memory. This is done on demand. And the cost of this is pretty substantial. Once a page has been committed, however, memory transfer rates can reach their peak performance. There's no way around the cost of initializing newly allocated memory, but you can't avoid repaying that cost by reusing allocated blocks as much as possible. For example, if you've allocated an array to hold temporary values, try reusing this array in the next round of calculations. On a global scale, you can try writing your own memory manager. This guarantees that the pages are never handed back to the operating system and always left committed, and therefore you never repay that initialization penalty. A hybrid approach might be to write a memory manager that only allocates large blocks of memory, say greater than 512 kilobytes, and then let the operating system handle any allocations smaller than that. This potentially makes the implementation of your memory manager much simpler, but can provide a great benefit to the larger calculations in your application. Bottleneck number 3, not properly inlining functions. Modern compilers are very good at rearranging instructions into optimal execution patterns, as well as vectorizing computations on large data sets. But they can only do this if they have blocks of execution that are large enough to work with. Inlining functions gives your compiler large blocks of code to work with, and it also avoids excessive function calls. Calling a function requires pushing all the local variables onto the stack, which in itself is very expensive. Bottleneck number 4, excessive conditional logic inside loops. It's easy to think that an if or a switch statement inside a loop won't cause any problems and that the calculations themselves will be the bottleneck, but this isn't necessarily true. There are 2 bad things that conditionals do to loops. The first is a compile time issue. When the compiler assembles the code, it tries to create execution blocks that can be pipelined and parallelized as much as possible. Conditionals can prevent your compiler from doing this, and you'll be left with suboptimal assembly. The second issue occurs at runtime. During execution, the processor places multiple instructions into its decoder pipeline. If there's a conditional branch in your code, the processor must try to predict which branch will be taken. If the processor guesses incorrectly, it has to flush its execution pipe and start loading the instructions for the other path. This is called a branch misprediction, and it causes the execution pipe to stall. To prevent these problems, try placing your conditional logic at a higher level than your loops. By creating distinct loops without conditional logic, the compiler will be able to optimize and vectorize this code, and you'll avoid any branch misprediction at runtime. Sometimes you can use masks or zeros to avoid conditionals and loops. For example, suppose you needed to compute either a quadratic functional or a linear functional for every element in an array. Rather than do this with conditionals, you could store the coefficients of the quadratic for each element in the array, and then store zeros for the quadratic coefficient for those elements where you only want the linear value. Because of the way processors work, computing the full quadratic function would probably be much faster than executing a conditional inside a loop. In addition, virtual calls should be avoided inside tight loops for similar reasons as conditionals. The overhead of calling a virtual function is only about 10 CPU cycles, but a high-end CPU with proper vectorization and optimization can actually accomplish quite a bit in that time. So a delay of 10 cycles per iteration in a tight loop actually carries a large overhead. Additionally, virtual functions can't be inlined, and this impairs the compiler's ability to optimize your code. Taken together, these 2 issues with virtual functions can have serious impacts. So if you need runtime polymorphism, try to implement it at a higher level in the call stack outside of loops, where the overhead of a virtual function call has less of an impact. You might also try using compile time polymorphism using C++ templates. Bottleneck number 5, non-sequential memory access. Processors are most efficient when they can read in many elements of data, one right after the other. They do this by prefetching data blocks through multiple memory channels and funneling it into the compute cores as quickly as possible. If there are large gaps in your memory accesses, the processor can't do this and your performance takes a hit. The larger the strides, the larger the hit. In the worst case, your jumps are so large that you miss all caches and you have to reach into main memory. This is called a cache miss. When this happens, your compute cores sit idle for many cycles until the data they need finally arrives. Doing this repeatedly destroys performance. Now, different processors have their own unique cache characteristics. So when designing your data layout and your data access patterns, try to take these into account. Bottleneck number 6, writing cache-unfriendly code. The phrase cache-unfriendly code is a fairly broad term, but I'd like to distinguish this issue from the previous issue because a lot of times your data access patterns won't permit contiguous reads. So here I'll provide a brief overview of memory hierarchies, and then maybe in a future video I'll go into more depth. So CPUs, GPUs, and other high-end processors all contain some sort of memory hierarchy. The part of that hierarchy that's closest to the processor is called the L1 cache. It's the fastest part of the hierarchy, but it's also the smallest part. For example, the latest high-end Intel CPUs have a 48 kilobyte L1 data cache. The next closest memory is called the L2 cache, which is larger but slower than the L1 cache. And this keeps going out until you reach the main memory, which is the largest block in that hierarchy, but it's also the slowest. When the processor needs data for a calculation, it first tries to find that data in the L1 cache. If it doesn't find it there, it goes out to the L2 and so on until it finally finds it in some part of the memory hierarchy. The further you go out, the longer it takes to find that memory and the longer it takes to bring that back into the processor's registers. Obviously, the best performance is achieved when the data resides in the L1 cache. So an important question to ask is, how does data get into a cache? Well, the answer is pretty simple. Whatever was last used gets put into the cache. Unfortunately, if something's already there, it has to push something out in order to make space for that data in the cache. This is called an eviction. And the cache will evict whatever was used the longest time ago. This is called the least frequently used principle. So now that we have an idea of how memory hierarchies work, what kinds of things would lead to cache-unfriendly code? There are two things that hurt cache performance. Number one is large jumps in data access patterns. Number two is code that causes too much data to be evicted from caches. The gap between two subsequent memory accesses is called the stride. Without going into too much detail, the basic rule is that the longer the stride, the longer it will take to retrieve that memory. It's not a linear relationship, but it's an important idea to keep in your mind when you're organizing your data. So if you have a block of data that you expect to access frequently, maybe a table or a search tree, you want to make that data as small as possible and packed as tightly as possible to minimize your strides. For the second issue, recall that data is evicted from the cache when the processor detects that that piece of data is the least frequently used. But if you have code that cycles through a lot of data, the least frequently used part might be the first part of that data. An example of this is a for loop that cycles through one or more large arrays. Recall that the L1 cache on an Intel CPU is only 48 kilobytes. If your array is larger than 48 kilobytes and you're looping through that array multiple times, you'll never hit the L1 cache because by the time you get to a certain point in that array, the first part of that array will have been evicted. To resolve these issues, ask yourself the following questions. 1, how can I reduce the size of my data? Number 2, how can I arrange data to be packed more closely in memory? And number 3, how can I organize my code to reuse data? Unfortunately, the answers to these questions depend on the particulars of the algorithms and the data structures being used. But the important point is just to be aware of this issue, to profile your code to see how much of a problem it is, and to organize your code in a way that alleviates the problems as best as possible. In the future, I'll put together a video that goes into more depth on this topic. Bottleneck number 7, not parallelizing your code. Just about every computer, phone, or tablet has the ability to run multiple threads or multiple processes at the same time. Many laptops can run 4 or 8 processes simultaneously. High-end workstations can run nearly 100 processes in parallel. And GPUs can perform thousands of calculations in parallel. So if you're not taking advantage of this parallelism in some way, you could be leaving a lot of performance on the table. The most optimal parallelism occurs when many operations are done in sequence without any form of communication. For example, this occurs in graphics processing when individual pixels are drawn on the screen. High-level graphics APIs abstract away the details of this parallelism, and all you need to worry about as the programmer is making the right calls and passing in the right parameters. In engineering applications, however, parallelizing your algorithms is usually not so easy. Engineering simulations often involve calculations over a continuum, like a solid or a fluid, and typically require solving systems of linear or nonlinear equations over that continuum that describe the physical variables of that system over space and time. Solving non-trivial problems with sufficient resolution and accuracy often must be achieved through parallelism. This is why engineering simulation software can be very complex and often carries a high price tag. Due to the cost savings that simulation software can offer over physical prototyping, usually makes it worth it. Bottleneck number 8, excess parallel communication and synchronization. Whether your parallel program is sending data or just synchronizing, either of these operations requires some form of parallel communication. At this point, all processes that have completed their work must stop and wait for all the other processes to complete their work and catch up to them. If these processes have to wait too long, valuable compute resources are just being wasted. To avoid these types of bottlenecks, you want to find ways to do as little communication and synchronization as possible. Unfortunately, the specific techniques for achieving this are very problem-dependent and require more in-depth discussion of those specific problems. Bottleneck number 9, poor load balancing in parallel. Work between processes must be distributed so that all processes have roughly the same amount of work to do. If they don't, then some processes will finish early while other processes will take longer than they should have. This concept is known as load balancing. A simple example of this is, suppose you want to compute the sum of an array using 4 cores on your computer. Obviously, the best way to do this is to take the array, divide it into 4 equal parts, and then have each core work on each part. When you're done, you get a partial sum on each core, and then you do a global synchronization and sum up those 4 partial sums into a global sum. But if for some reason one process was given 90% of the data, then this process will take 10 times longer than these other processes, which will finish early and sit here and wait for this process to finish its work. This would result in the overall execution time being greater than if all work had been distributed evenly. Unfortunately, load balancing is not always as straightforward as this particular example. Depending on the structure of the data, equal distribution of elements won't necessarily result in an equal distribution of load. For example, let's suppose we want to compute the areas of 2 million polygons on 2 different threads. If I naively divide all the polygons equally between 2 threads, then one thread might get 1 million triangles and the other thread might get 1 million octagons. The thread with the octagons will take about 6 times longer to complete than the thread with the triangles. So for this problem, we would divide the elements unequally and take into account the cumulative load that's done on each thread. In general, a load balancing scheme is going to depend on the type of the data and the operation being done on that data. Unfortunately, there's no general cookbook formula that will work in all situations. The important thing is to recognize the problem and find a way that evenly distributes the work as much as possible. Bottleneck number 10, excess network communication. These days, more and more applications are running on either a web browser or a mobile platform like a tablet or a phone. And these applications are usually just a front end to a remote database that resides somewhere on the cloud. While these applications provide excellent data portability, their big disadvantage is that they can get bogged down by a poor internet connection. Even with a good connection, accessing data over a network has much higher latencies and much lower data transfer rates compared to the memory or even the hard drive on your local computer. And the worse the connection, the less responsive the application is, and the worse the user experience. One simple and effective approach is to simply cache data that is frequently used on the local device. An example of this is the GPS application that I use on my phone. Everything, the maps, the GUI, the waypoints, is all downloaded and stored on my phone. So I can use it while hiking in the mountains without any internet connection at all. The only thing that it needs to connect to are the GPS satellites that it uses for navigation. An example of an application that doesn't use caching very well is one of my music streaming apps. It allows you to download the playlists, but it doesn't cache the front end used to access the playlists. So if your cellular connection is not very fast, the application itself is very unresponsive and very difficult to use. So while I like the app and I like the music selection, this one issue causes a very poor user experience for me. Okay, I know this has been a lot, and I feel like I have just superficially touched on each issue. Each issue really deserves a dedicated video, and I will try to address each topic in turn in the future. But I wanted to make sure that I've covered all the major bottlenecks that I've encountered in my 25-year career in software development. I hope this video is helpful. If you have any questions, comments, or ideas, please leave them in the comments below. I'll be making more videos on software performance analysis, optimization, and programming in the coming weeks. So if you're interested in this topic, please subscribe. Thank you very much, and I'll see you again soon.